everyone. This presentation is towards Angular Rack. I'm Carlos Onielfa, and I'll be sharing a small experiment I did last year, trying to answer the question, can we assess token-level relevance with these embedding models? So yeah, as I said, I'm Carlos Onielfa. I'm a machine learning engineer at Progress, and I work mainly in the Progress Agentic Rack product, where we offer Rack as a service. So, as I'm sure you all know, text embedding models are portals. They are portals between the text space, the words, and their meaning, or that semantic space. This is what has enabled us to power semantic search, and it's super nice. But one thing we have to take into account is that we have limited ourselves to retrieving chunks. It would be super attractive if there was a retrieval paradigm in which we made it possible to retrieve text at any size, and we're not limited by those arbitrary chunks we chose at ingestion. So I went and I tried to explore this direction a little bit as an experiment. And yeah, one thing to take into account is that all embedding models we already use already generate token-level embeddings. It's just that we are discarding that information, and we'll see that after. For this experimentation, I tested several models, but one of the core limitations towards exploring this a bit more was context windows. At the beginning, these semantic models had only like 512 tokens, which is super small. But nowadays, models with about 8,000 token context windows are commonplace, and there are some, like Queen3 embedding, that can get up to 32,000 tokens, which is massive, and enables us to very easily embed whole documents in a single pass. This is due to this model specifically being created from an LLM, which has already seen a lot of long context data. So that's our model. Then moving on with the example document I'll be using. It's a super technical document about a very complex device, which is the SpongeBob laptop from Nickelodeon. It's about 14 pages, fairly simple text. Here you can see the specs, like the 64 gigabytes of RAM, all that good stuff. And then you also get some information about the games you can play on it. I'll draw your attention to this one right here, the Weighty Food game, which we'll be using to test a bit how this approach works. Moving on, how we'll be getting those token level embeddings. So when we do like the sentence embeddings, what we'll do is that we tokenize our text, of course, and then it goes through all the layers of the model, and we'll do what's normally called pooling, so just getting a single vector for that sentence. It depends on the model, but for Queen3, the method of pooling is just taking the embedding for the last end of text token, which is added automatically when tokenizing. For some other models, it's taking the vector for the first one, for the start of text token, and for others, it's just like doing the mean over all the tokens. So yeah, if we want an embedding for each of the tokens, it's just as easy as taking them all, and not only the last one. And then, how do we score them? Traditionally, if you are using sentence embeddings, you have a vector for the sentence, a vector for your chunk, and you compute their semantic relevance using normally the dot product, which would be equivalent to the cosine similarity if they were normalized. And now, in our case, it's the same, but instead of vectors, we have matrices. If we stack those embeddings, we get a matrix for the query and a matrix for the document, and getting that relevance is as easy as just multiplying both matrices. This makes it so that we are doing that dot product for each of the vectors. We can then visualize that relevance matrix, and it may look something like this. Traditionally, if we were, again, with the normal approach, what we'll be doing will be comparing this end of text token with the end of text token for the document. So as you can see here, like the vertical axis, the y-axis is our example query, what game makes me reason by weighing objects, and then along the x-axis will be the tokens of the document. So from page 1 until 14, and as I said, that end of text token, and the normal approach will be just looking at this sliver of value, like right here, super small, and you can see how much information we're losing by going that route. We have much more data here that we can work with. And one thing we have to take into account as well is that we are interested in the relevance of the whole query along the document tokens. So we need a way to summarize the query or have just a single value for the whole query. This is thanks to the approach that Qwen3 uses. It's as easy as just taking the last token for the query and focusing our attention down to that single row. Here, we can start to see some stuff, like the brighter values are more relevant values. We can see some parts that are clearly brighter. But if we represent this as a line graph, it becomes much clearer. Although we can see that there's a bit of noise, right? It's not a super nice relevant signal. So when I saw this, I wanted to dive a bit deeper into what was going on the token level relevance, and I found something a bit interesting. If I looked at the relevance for each of the tokens in a sentence that was meant to be relevant to the query, I noticed that the high relevance was being focused towards end of sentence markers. And for instance, for this sentence, you can see that the period has actually the higher relevance. For me, like this intuitively points to this attention that the model uses. Since it's based on an LLM, it uses causal attention and not bidirectional attention like other encoder models, or like encoder models, since this one is the coder-only model. And that makes it so that the model is encoding that relevance at the latest tokens. And that also follows the way it was trained, because it was also trained to encode the relevance into that end of text token at the end of the document. And we might be seeing that same phenomenon, but at the end of the sentence. So with that, now the noisy signal is has a bit of an explanation behind it, since we expect to see those noisy peaks. Taking that into account, I devised an algorithm that could help us get those relevant areas of the document given our query. As a bit of a recap, this is another example. It's not about SpongeBob. I'm sorry, we'll get back to SpongeBob in a short while. And so here we're embedding the query, as we have seen. We'll need to do that as well for the document. Here's a super short document as an example. You can see the tokenization, adding that end of text token. As I've said, we can compute the relevance within them with that relevance matrix, which we can visualize here. We are only interested in that end of text token for the query. We focus our attention down to that, and we plot it as a line graph. Here is where we are up until this point. Now, with that information about the peaks, what we can do is set a threshold above which every single value will be considered a peak. And we can cluster together peaks that are close together to get those relevant spans. And finally, once we have those sections that are supposedly relevant, we can expand them to full sentences. That's the main idea behind it. A couple more notes is that I found that it worked a bit better if you previously applied some smoothing to the relevant signal. In my case, I tested several methods, and the Gaussian smoothing seemed to work the best. And finally, we also need a way to score those relevant spans. And also, as well, doing some testing, I found that taking the max value of the relevance, so the highest peak on that span, was what worked the best for getting that relevance score for each span. And if we look at the result of applying that algorithm for the example query I showed before, in light gray, you'll see the raw relevant signal, which is super noisy. And the dark gray will be the smoothed out relevant signal. Then the dashed line will be the relevant threshold above which everything is a peak. And then with this salmon color, you can see highlighted the spans that were found to be relevant. If we look deeper and go into the text that was actually found on those spans, for this example query, what makes me reason by Boolean objects, we can see that the span 1 with the highest score has the interesting game I talked about, that way food game. And the second one also has some words that might be semantically meaningful to the query because it talks about math. So that's nice. Let's now see some more results for more queries. And this is the similar graph as before. I've just added the ground truth sections for the spans we're aiming to retrieve in blue, when they overlap with a salmon section, they show up as purple. For the first one, as we've seen, we do retrieve the interesting part of the text. For the second one, the display is too bright. What can I do? Amazing retrieval. We get that pinpointed exactly. So another query. What type of battery does the laptop use? In here, also we get the relevance section, and I also checked that last section, and it turns out that this was also talking about batteries, because in the next query, which is the laptop's not starting, what can I do? Actually, one of the troubleshooting steps is something like check if the batteries are there and if they have charge. So it seems to work great. But now let's move to the sad part of the presentation, the drawbacks. First up, what I talked about, this causal attention and how we might be interpreting as encoding that relevance on the end of sentence markers, it might actually be playing more tricks on us than we think. Why? Let me show you. If you go to these relevant signals again, you'll see that all of them ramp up towards the end. Like right here, there's a ramp up, and here as well. They all go up towards the end. So I think this might actually be indicating that this phenomenon is happening not only at the sentence level, but at the whole document level as well. And this might imply that if your target span is at the start of the document, it might be underrepresented in terms of relevance, and if it's towards the end, it might be overrepresented, which is a drawback, of course. Then, I haven't talked about this, but obviously this model is producing 1,000 dimension vectors for each of the tokens, which is massive, and it's not feasible in production. And finally, this algorithm, of course, there are values like thresholds and the spawn boundary markers and other that are hand-tuned. You could probably learn them or try to find optimal values, but there's no guarantee that a single value will work for all types of data or languages. That's a big unknown. So yeah, those are the drawbacks. And yeah, I'm sure many of you already know of other types of models that could maybe help us on this. And those would be Colbert models. Colbert models would probably fix point 1 and point 2. But during my experimentation, I tested them. And in fact, I started it with Colbert models. I tested all the models that were state-of-the-art when I was in the experimentation last year. And all of them underperformed compared to Qwen3. So when I was about to close the experiment, Gina released the Gina embeddings v4 model and actually tested that one, and it showed promising results on the example query. So I went ahead and did some more testing. As I said, they already use those token level embeddings, so they are good candidates for this task. And Qwen gave us that end of text token, which made it super easy to have a relevance signal for the whole query, or a relevance value, let's say. And Colbert doesn't give us that. I did some testing, comparing different methodologies, and aggregating like the max relevance for the query made it work. Follows also the intuition that these models are trained with the for the maximum similarity, so I went along those lines, and yeah, it worked the best. But then I checked the results. As I said, for the first one, worked great retrieval. But there were queries like this second one, where the relevant signal completely broke down. As you can see here, there are no peaks, it's a super flat signal, and nothing goes above the threshold, which is strange, but it is what happened also with the other models that I discarded, so I don't know what's going on there. It's a shame, because for other queries it does work great, but yeah, not only for this one about the display, but some variants of this query also gave disastrous results. So, in conclusion, the Qwen3 experiment proves that the information, the signal is there, and the methodology could work, but there are clear issues regarding the storage and that decoder bias or that causal attention bias, which is a big unknown. Then, the Colbert models, of course, seem better suited to the task, but they are yet to show performance at the same level as Qwen3, which is a shame. And as clear next steps, I would say, like, this was done a year ago. I'm sure new Colbert models could perform a bit better. Let's see if they break that barrier and bring us up to the performance we expect. And finally, of course, these models have not been trained for token level relevance, any of them. And the fact that they are able to encode that relevance into those tokens is just a byproduct of their training. And if we actually supervise the model to encode that relevance properly, maybe we could see some way better results. So yeah, that's it. Thank you everyone for coming. And in this QR code, you'll find the full blog post with more details and the code which you can yourselves. And if you want to have a chat, you can find me during the conference or connect with me in LinkedIn. That's it. Thank you.
Thank you, Carles. Are there any questions? We have 2 minutes.
Thanks for the talk. Very nice. Do you know why the Quen model is slightly more biased toward the end of the sentence and the end of the document?
I do not know for sure, but I think it's also a byproduct of its training, as we can, as I've seen or as I've shown. Sorry, it was trained to encode the relevance to that end of text token. So it was trained to encode the relevance at the end of the sentence, and I think that's like a byproduct of that is that of that training and also the attention, which goes hand in hand. It's a causal attention. It's not bidirectional, so it goes from left to right. So it's when like tokens are arriving like sequentially. So when a token, like maybe the sentence ends, like the model now has the context for the other part of the sentence, and now is able to encode that relevance into the period or new line or whatever.
Well, congratulations for the talk. Felicitats. My question is related to the corpus side of things. What happens or what problems do you envision when you find like heterogeneous corpuses? Like not all the documents have like 14 or 15 pages, but you have a corpus where one document might have 20 pages and other document might have 16,000 pages. Do you think that this kind of chunkless rack approach would scale linearly to what you're proposing? That's all. Thanks.
Thank you for the question. The thing is, well, for this document, it's, as I said, 14 pages, a bit light on text, but that would be about 3,000 tokens. This model accepts up to 32,000 tokens, so you still have room for like 10x the amount of pages, approximately. But of course, there are documents that won't fit in these bounds. So you'll need to do like will still be chunking, just at a higher level, right? Probably with a sliding window approach, something like that. You could still embed all the tokens. You'll be losing some of the context, of course, but I think it's not a big limitation, aside from the concept of like the threshold tuning and stuff like that, which still could be brittle and break.
Yeah, so we are running out of time. Thanks again. And see you on the next talk, and you can talk to Carles, I guess.